Hi, I'm Brian Freer, tutoring high school physics. Today's topic, kinematics in 2 dimensions. So here's a kinematics in 2D problem. We have Jimmy throwing a ball at 5 times the square root of 2 meters per second at an angle of 45 degrees to the horizontal, and it strikes Dean. Assuming that the ball strikes Dean at the same height at which it is thrown, 3 questions. How much time does it take to hit Dean? What is the distance from Jimmy to Dean? And what is the ball striking velocity? Well, before we start, first off, there's the golden rule of kinematics, or really anything in 2 dimensions. That which happens in your x dimension is separate from what happens in your y dimension. So all the kinematics of the horizontal dimension are separate from those in the vertical dimension. So that means we're going to write out 2 sets of variables, one for the x and one for the y dimensions. So let's actually get down to that. First step, write out your variables. So your final x position is unknown. Your initial x position is also unknown. Now we're actually going to try to solve for these later on because we do want to know the distance between Jimmy and Dean. But let's move on with our variables. Our final velocity in the x dimension is unknown. Our initial velocity in the x dimension is also unknown. Our acceleration in the x. Well, this we do know because nowhere in the problem is indicated that there's any acceleration in the x dimension. So we're going to put that at 0 meters per second squared. And finally, there's time, which we don't know, but is shared between the x and y dimensions. Onwards onto the y dimension. So, our final y position, we don't know its numerical value, but we do know this. It is the same as our initial y position. Well, how do we know? We're saying that the ball is going to strike at the same height at which it's thrown. So its position in the vertical at the beginning of the ball being thrown is the same as its position in the vertical at the end of the ball being thrown. So our final y position is the same as our initial y position. We could also say that the displacement in the y dimension is going to be equal to 0. Okay, so let's move on. Our final velocity in the y dimension is unknown. Our initial velocity in the y dimension is unknown. Our acceleration in the y is negative 10 meters per second. So you might be wondering where I got that. Well, we're going to assume that this problem takes place on Earth. Unless it says it takes place somewhere else, or it gives you a specific acceleration due to gravity, we can assume that in the vertical dimension, gravity is acting on whatever's happening. So in this case, the ball is going to be thrown, gravity is going to pull it to the ground. Now notice I've given this a sign that's a minus sign. This is just convention. Minus is typically going to be down, whereas positive is going to be up. Now, for the x dimension, right is typically going to be positive, left is going to be negative. Again, this is conventional. As long as you keep your signs in mind, it doesn't really matter. Okay, finally, time is shared between the x and y dimensions. Alright, so next up, second step, split up your vectors. So we actually have a vector in this problem. We have this ball. It's being thrown at an angle. That means it's not being thrown solely in the x or y dimensions, but we can split it up. Basically, any line you see that is at an angle, you can split up into a right triangle. So this is my right triangle. It's very attractive. 45 degrees. And here's our 5 times the square root of 2 meters per second. If we find out what these two legs are, we can get our initial velocity in the x and y dimension. Recall that the sine of an angle is the opposite leg over the hypotenuse. If we then multiply the sine of an angle by the hypotenuse, we eliminate that particular part of the problem, and we're left with just the opposite leg. So 5 times the square root of 2 times the sine of 45 degrees is going to give us this leg, which is just 5 meters per second. And that's our initial velocity in the y dimension. So let's also do that for the x dimension. This time we're going to do cosine. So cosine is the adjacent leg over the hypotenuse, but multiplying by the hypotenuse again gets rid of that term from the end result, leaving us with just the adjacent leg, and that's also 5 meters per second. Additionally, you could note that this is a 45, 45, 90 triangle and just apply the ratios. So here we have our initial y velocity, let's write that down, and our initial x velocity. This also gives us our final x velocity, because as we recall, there's no acceleration in the x dimension, so the x velocity doesn't change, and we're left with 5 meters per second up here. Now we actually have enough variables to solve one of our kinematics equations. So you should probably have these 3 memorized, or on a piece of paper somewhere nearby you. So we're going to solve this in the y dimension. The displacement in the y dimension is equal to our initial velocity in the y dimension times time plus 1/2 times acceleration in the y dimension times time squared. So we have 3 of the variables that we need, and we're trying to solve for the fourth, so we have 0 meters is equivalent to our initial y velocity. We're solving for time, plus 1/2 times our known acceleration, meters per second squared times time squared. And you'll notice that we've only got one variable we need to solve for, so we can actually solve this equation. For now, I'm going to start omitting units from this so we can see that it's actually quite algebraic, but do recall that the units are there. So we get 0 equals 5t, and so that's 1/2 times negative 10 minus 5t squared. So let's factor out the t. We get t times 5 minus 5t. So we do some algebra and we'll find out that there are 2 answers for t. T is going to either be 0 seconds or 1 second. Which one of these is it? Well, we're going to have to put this in the context of the problem. At t equals 0 seconds, no time has passed. The ball hasn't even left Jimmy's hand. This can't possibly be the amount of time the ball takes to strike Dean. That means we're just left with 1 second, which is in fact how much time the ball takes to strike Dean, given those speeds. So now we actually have enough variables to find out what our displacement in the x is. Okay, so we're going to solve this exact same equation except for the x dimension. Displacement in the x is equivalent to our initial x velocity, which is 5 meters per second, times our time that we've now found out to be 1 second, plus 1/2, times our acceleration of 0, times our time of 1 second. So since this acceleration is 0, this all just goes to 0. Delta x is equivalent to 5 meters per second times 1 second, so we get 5 meters. And in fact, that's all we need, because all we wanted to know was the distance from Jimmy to Dean. So we just found that out. We can actually just say that this is all now delta x equals 5 meters. Okay. So the last thing we need to find out, what is the striking velocity? Well, we started out with a velocity in the x and y dimension, so we're probably going to end with a velocity in the x and y dimension. When reporting this velocity, we'll want to combine it back into a hypotenuse, just like we took our hypotenuse apart, and also give its angle. So we're going to need to find out our final y velocity. Well, to do that, we again are going to solve the kinematics equation. Our final y velocity is the same as is equivalent to our initial y velocity plus acceleration of negative 10 meters per second squared times our time of 1 second. So let me actually quickly substitute in. This is going to be 5 meters per second. This is unknown. And so 5 minus 10 times 1, that's going to give us negative 5. So we have negative 5 meters per second. Okay, so then let's draw out our triangle. We have our x dimension, and that's going to be 5 meters per second. This hasn't changed. In our y dimension, now this is actually going to be drawn downwards because we defined y as a negative dimension. So down is the negative part of the y dimension. And so here's our right triangle. This is going to be 5 meters per second. And so now we can just use the Pythagorean theorem to find out what this is. And if we run through that, it's 5 squared plus 5 squared equals c squared. We solve for c squared and we get 5 times square root of 2 meters per second. And now all we have to do is a bit of trigonometry to find out what this particular angle is. And so as we recall, the sine of our theta, which is going to be this angle, is equivalent to the opposite leg, 5 meters per second, over our hypotenuse of 5 times the square root of 2 meters per second. And our theta is going to be 45 degrees. Okay, so now we've actually solved our problem. We figured out it takes 1 second for the ball to strike Dean. If there are 5 meters from Jimmy to Dean, and the ball strikes with a velocity of 5 times the square root of 2 meters per second at an angle of 45 degrees below the horizontal. Alright, to recap. When solving a 2D kinematics problem, split up your dimensions. What happens in your x dimension does not affect what happens in your y dimension. Now then there are 3 steps. First, write out all your variables, both in the x and the y dimensions. Next, take any vectors and split those up. Then add what you find to your variables. And finally, solve kinematics equations to get your answers. Alright, that's all for now. Again, I'm Brent Creer. See you next time.